So today we're gonna talk about a relatively simple subject, which is lists and arithmetic, how it is done in Prolog. Now, coming from functional languages like Lisp and Haskell, this shouldn't be very difficult. So let's try to get through this quickly. So before I begin, I would like to make a small clarification about complex terms versus predicate calls. I think this has been a little bit of a confusion, at least in the labs. So suppose we have this predicate called connected, right? Which just tells us whether two vertices in a graph, for example, are connected, right? And we define predicate path. And our predicate path would take three arguments. Two of the arguments are the source and destination. And the third argument is the actual path from the source to the destination, right? And if we start at some vertex and then we go to the same vertex, then there is a very simple path, like an empty path, which we just call stop. Now, another interesting possibility here is that if we have the source and destination already connected, which okay, yeah, I meant to have from to there. If we have from and to already connected, like by a single edge, then we can just, as our path, have a complex term called go with two arguments from and to. Now, what's important here is that go that we use here is used similarly to value or data. Let me double check. Yeah, I think battery is dead. Can you hear me now? I'm more interested in guys online, if they can hear me or not, because I'm not sure if this microphone.
Yes, we can hear you.
Okay, thank you. Okay, sorry for this. So yeah, what I've been saying is that go here is used sort of similar in a similar way to data constructors in Haskell. It's not a function that does something or a predicate that computes something. This is just a label for the tuple. So this is basically a labeled tuple that we're returning here. Okay. Now it looks similarly to how you would call predicates. And that's just the way Prolog works. It's similarly to Lisp, where everything is an ASCII expression, and you can use those as data or as function calls. Here, it's similar in the sense that, well, everything is a term, and you can have complex terms that are actual predicate calls, and you can have complex terms which are just interpreted as data. Okay, and so yeah, let me take this. And so if you have two vertices connected indirectly, right? So for example, connected, you say that from is connected to some other vertex called next, and then next has a path to the destination to, which we call path, right? And then we construct the result for from and to as go with three parameters from the intermediate thing and then the component of this go is going to be the path. Okay, and so just to see how this works, if we have path from 1 to 1, then well, that's going to be just stop. If we want to find a path from 1 to 2, then we will have as the result of this go 1 2. And then if we want to go from 1 to 3, then we can go from 1 to 2 first, and then from 2 to 3, right? And this is the result that is constructed. So just the clarification that I wanted to make is that go here, first of all, is just a label for the tuple. And it's fine that it has different number of arguments, right, for different cases. And it is not any kind of predicate. So you should not define it. I mean, you can have it defined, but it has nothing to do with any definition of go that you have in the code. Okay, does this make sense? Very good. So now today we're going to talk about lists and arithmetic, right? That's I already mentioned this. So first of all, syntax. Syntax is not very complicated. You have like this, similarly to Haskell. Now, the difference, of course, with Haskell is that in Prolog, everything is a term. So lists are also terms, and they can contain any terms in them. So you can have numbers, or you can have complex terms, or you can have variables, or you can have whatever you want. So it doesn't have to be just a list of numbers. It can be a list of anything. So you can have a list that contains an atom, a hello, a variable x, a complex term flight, which contains also a variable inside, and then a number, okay? And of course, you can have lists that contain other lists. And again, you can mix everything with everything, right? There is no rule to it. You can put everything together. So if we want to work with lists, what's sort of useful to us is this vertical bar operator. And it works a little bit similarly to cons in Lisp and in to the colon in Haskell. So when we have this, like in square brackets, head, vertical bar, tail. Now, head and tail are variables, and they match or unify with respectively the head and the tail of the list, which you already know what those are, right? So head in this case is going to be 1, and tail is going to be 2 and 3. Okay. Now again, importantly, head is always just one single value from the list, and tail is always a list, like the list of the remaining elements. Okay. Now, what you can do in Prolog is you can put multiple variables separated by commas on the left of the vertical bar, and that would mean, well, that you just want to match more than one element on the left, right? And in Haskell, you would just put multiple colons before using the tail. So first is 1, second is 2, and tail is 3, 4, 5. Okay, easy, very good. Let's move on. Now, sometimes you need to reach to certain elements in the list or in a complex structure, right? But you don't want to to give a name to everything in your complex pattern. So that's when you can use the anonymous variable, which is just the underscore. Okay, that way the compiler just, well, it matches it with something, but different underscores are treated as separate variables, not as the same one. And then, yeah, basically, you cannot use them. You just say, well, whatever can be in that place. Okay, useful construct, useful in many places. We're going to be using those in examples from now on. Now, let's define a very simple predicate on the list. Predicate is called member, and the idea is that it checks whether the given element occurs in a given list. Okay, so the simplest corner case that we can, or base case that we can give to this predicate is say that, well, if we have a variable x and we have a list containing that variable x, well, then that is true, right? This is how we write the base case for the member. But we can actually make this a little bit more general, right? we know immediately if an element is a member of the list if this list starts with this given element. It doesn't have to be like a singleton list. It can be any list that starts with an X and then has whatever as its tail, right? The syntax is clear? Okay, very good. Now, the recursive case is, of course, if we have a tail, then X can also occur in the tail, right? Very simple, very easy. So let's see. If we have a list of A, B, C, D, and we check that C is a member of that, well, that's obviously true. Now, importantly, in Prolog, you can put variables everywhere, right? Everywhere you want. Sometimes it works, sometimes it doesn't. So what do you think happens if we put a variable as our first argument? So what do you mean all elements of the list? Yeah, so there will be four distinct solutions to this question. Yeah, and the first time you will get A, and then if you backtrack, you get B, and C, and then D, etc. Right? So remember that we're talking about predicates, but in Prolog, because of the backtracking and unification, we use these predicates for various purposes. We can do them as checks, or we can do them to, in this case, to iterate over elements in a list, right? And then use this X later in something. So this is essentially, you already have some sort of loop construction. Okay, before we go to other functions on lists, we need to introduce arithmetic. Well, not for all of them, but it's handy. So arithmetic in Prolog is, if you remember, you cannot just unify 8 and 6 plus 2. Those are different terms. To sort of check whether 8 and 6 plus 2 are equal, you have to use this predicate is. And what is does is it computes the thing on the right, essentially. So 8 is 6 plus 2. That's the answer is yes. 12 is 6 times 2. Yes. So this is all very straightforward. The only thing that you have to remember is that is the predicate that you use for arithmetic, and you can have a complicated expression on the right, which gets computed. Yes. Yeah. Yes is the same as true. Yeah, it's just yeah, some versions of Prolog output yes, some output true. It's the same thing. Yeah. Now, maybe important, might be important for you to know that there is also mod. So the slash is for division, but in Prolog, there is essentially, as we talked before, we're mostly concerned with integers. So this is an integer division, and mod is written this way. Okay, very good. Now, obviously, it's a term. It's a complex term of 7 and 2. It's so again, I mean, plus also is not a predicate, right? Because it doesn't have the return argument. It doesn't have the return argument. This also doesn't have the return argument. So what you have on the right of is essentially a syntax tree built of terms, which is computes to a certain value and then unifies that with the left-hand side. Okay, does that make sense? So what happens here? So X is 6 plus 2. Well, again, we compute the right-hand side and we unify it with the left-hand side. We get X equals 8. Beautiful. Can we use variables on the right? Well, unfortunately, we cannot, because if we have a variable that we don't have the value for, the instantiation for, then we cannot compute the right side, right? And then you get this sort of not very beautiful error message that tells you that arguments are not sufficiently instantiated. Okay, so again, if you want to use is, the right side have to be, well, known. Now, This doesn't mean that you cannot use variables on the right side. You can, for example, define this silly predicate, which says that x is essentially 6 plus y, right? And you can call this predicate as long as whenever you get to sort of computing the result of is, you know the value of y. So in this case, we know that y is exactly 2, so we know how to compute is, so everything is fine. We get x is equal to 8, right? But it's very important to keep in mind that if y is not known at the time of computing the value of is, then you will get an error. Okay. Okay. Very good. So now that we know basic arithmetic, how do we compute the length of the list? Well, if the list is empty, the length of that list is 0, right? If the list is not empty, then what do we do? Recursive call, yes. So we compute the length of the tail, which is some other number, m, for example, right? And now we need to relate the numbers n and m somehow. And for that, we're using arithmetic, right? So notice that we cannot write something like length of non-empty list is n plus 1, where on the right hand side, you do the recursive call, right? N plus 1 is not a valid like pattern, right? You have to use is to make sure that you do that arithmetic. Okay. Now, it is very important that we put n is n plus 1 after the recursive call. Why is that important? Exactly, because Prolog, when it will compute the result of length for some list, right? If we do the is predicate before length, then m is not known at that point, and we will not be able to compute it, so we'll get an error. Okay, does it make sense? So we'll put n is n plus 1 after. So length works in trivial way, which I show here. Any questions about this? No? You don't know? I mean, should be easy, but if you have any question, let me know now. If we put it before the recursive call, right, then when we compute length of this list, right, we go to the second equation, sort of, right? And then we see, okay, now we can match the tail is the list BC, and then the number n, right, is m plus 1. But m is not known at that point. So the predicate is immediately fails, right? And then we never go to the recursive call. Does this make sense? Yeah. Okay, so let's look at this example. So this is a very simple predicate that essentially defines the binary numbers represented as lists of zeros and ones, right? A singleton list of 0 or 1 is a binary number, and then a non-empty list is a binary number if it starts with 0 or 1, and then the tail is also a binary number. Does it make sense? Very good. So now, if we have this definition, what happens if we ask this question? So think a little bit and tell me what is the first solution if there is one. Okay, that's a guess. So the first thing is going to be 0, 0, 0. Does everybody agree that the first answer that Prolog will output is going to be 0, 0, 0? Probably. Okay. Okay, let's see. So the first answer is indeed 0, 0, 0. Okay, so far so good. What's going to be the second one? Is there going to be a second one? 1, 0, 0. Come on, guys, you should be able to compute this in your head. Just take a second. Think. Okay, you got it? So who thinks it's going to be 0, 0, 1? Okay, who thinks it's going to be 1, 0, 0? Who thinks there's going to be a failure of some sort? Okay, nobody thinks that. Okay. Indeed, you just go for the next number. Okay, what's the third one? 0, 1, 0. Okay, how many of you think that there's going to be 0, 1, 0? Yeah, quite a lot of you. Okay. What other options are there? Yeah. 0, 1, 1. Okay. What other options can be there? No other guesses? Okay. Abdelrahman, you didn't vote for 0, 1, 0. What do you think? 0, 1, 0? Okay. Well, it actually loops indefinitely. Okay, so why does that happen? Right. So, okay, so you can actually see what happens in Prolog if you sort of trace how the search process is going. So to do that, there is a special sort of thing in Prolog called trace, which you can run and see step by step how the evaluation process of Prolog is happening. So if we start with this thing, it omits a bit more information that I'm giving here, but the important bit is that the first answer that the first predicate returns exits with is a singleton list with 0, right? This is the first binary number produced by this first predicate. And of course, it doesn't have the length 3, so length fails and we backtrack, right? We backtrack and we go to the second binary number that's generated by this thing. Second binary number is 1, right? Okay, this is also not of length 3, so we fail and backtrack. The next binary number is 0, 0. So far seems logical, right? Of course, that also fails. Then we have 0, 1, which also fails. What is the next number? Yeah, so if we go back to the definition of binary number, you can see that the third line of definition of binary tells us that, well, if it's not a singleton, right, then it's a non-empty list starting with 0 and with a recursive call for binary there, right? So you can see how when we are going for this recursive call, our first choice for a non-trivial list is also going to be this third line, right? So all binary numbers that are going to be generated by this definition are going to be some number of zeros ending with 0 or 1. Okay? It's going to be either 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, sorry, I cannot speak, I guess. After 0, 1, you will get 0, 0, 0, right? So again, because you're backtracking to what was the tail of the list where you have the first digit 0, right? And the recursive call again gives you, well, all the previous results that you will have already seen, which is 0, 0 and 0, 1. Now 0, 0, 0 is obviously of length 3, right? So this is our first result. Then we get 0, 0, 1, which is also of length 3, which is our second result. But the next number that we try, the next number that is generated by binary is 0, 0, 0, 0, a list of length 4. right? And then, of course, that fails. The length, again, the same one with ending with 1 fails, and then a list of length 5 fails. And we try that, well, for infinitely many lists until we run out of, I don't know, stack or memory, something. Okay, does that make sense? Very good. So if we want to do all of these numbers, binary numbers of length 3, right, of 3 bits long, how do we do that? Well, it would be a nice idea to sort of have the length predicate used first, for example, right? And what we would mean by that is, if we say length x3, would mean, well, x is some list of length 3. And now if we know exactly the length, exactly the structure of this list, we'll go and into the recursive calls only finitely many times, because we'll reach an empty list or a singleton list very quickly, right? Now, the problem is the definition that we wrote. Let me just go back to this length. The definition that we wrote, if we use this definition and we say length x3, what happens is we have a length of, for a non-empty list, because 0 is not 3, right, is length of something m, and then n is m plus 1. But if we don't know the list, then we don't know the m, right? Does it make sense? So we would like to sort of go the other direction. If we want to start with the length of the list, then we would like to infer, well, the structure of the list. But because this arithmetic is works only in one direction, right? It can only give us n if we know m, not the other way around. Because of that, our version of this predicate will not work. So if we just provide the length, the desired length for the list. So if you do a little bit more advanced Prolog, then you can define it in a proper way. Or alternatively, you can, well, there are some tricks that you can do, but they're non-trivial. So instead of doing that, we're using length as defined in Prolog. So it's as defined by default. Now, the default version of length is a bit special, and it can indeed generate a list of variables of a given length, essentially, right? So length x3, if we say that, then we immediately know that x is just a list of three values, and those values get fresh variables, which are then unified with whatever comes next. And if we define it like this, now everything works. We get, again, 0, 0, 0 is our first thing, but we never go into generating binary numbers of length 4. In fact, we only generate binary numbers of length exactly 3. So that's why we generate all of them. And at the end, after the last number, we actually get false, because there are no more solutions, and we know that there are no more solutions, right? We indeed traverse a finite space of possibilities here. Okay, does it make sense? Okay, very good. So if length is fine and you understand how length works in this binary thing, then let's go to appending lists. So if we want to append to lists, again, we have a predicate of arity 3, because, well, the first 2 arguments are the list that we want to append, and the third argument is the result, right? Okay, now again, similarly to how you would do this in Racket or Haskell, you just define it recursively, right? The simplest possible case is when one of the lists is empty. So if the list on the left is empty, then the list on the right is the result of concatenation, right? Very good. Now, what happens if the first list is non-empty? Well, if the first list is non-empty, you know that the result is also going to be non-empty. And moreover, you know that the first element in the result is going to be exactly the same as the first element in the left input list. Does it make sense? And so you know that. And now you have the tail of the left list, X, the second list, Y, and the tail of the result, Z. How are they related? How are they related? Yeah. Yep. So the tails are related easily. You just append X to Y and you get Z. Should make sense, but let me know if you have any questions here. So again, we treat the third argument as the return value, right? Right now. So the inputs are the first two arguments. And if the first input is a non-empty list with head H and tail X, right? Then we get the result list by having H, and then Z is going to be the result of appending X and Y. Yeah, a question? So append here is like plus plus in Haskell. It takes two lists and outputs a list. It just glues the lists together, like adding two strings together, for example. Does it make sense? So here's an example. Maybe maybe this will clarify things a little bit. If we have a list 1, 2 and the list 3, 4, then the result of their concatenation is going to be a list 1, 2, 3, 4. Okay. And again, you can probably see how this works. You get the first element of the result is going to be the first element of the left list. Then you go into the recursive call. The second element is going to be the second element from the first list, which is 2. And then you go into another recursive call, right? And then you have append empty list 3, 4, and whatever is there. And then you return 3, 4. So that's how you get 1, 2, 3, 4. Okay, makes sense? Moving, yeah? Why not what? Well, in our definition, we say that if the list on the left is empty, then we just return the second list, right? Are you confused with with how it should be, or with the definition that we have written? So append here works as it just takes two lists and concatenates them. It does not take a list and add it as an element to another list. It concatenates them instead. It's like plus plus in Haskell, or it is like I believe it's called append in Racket. Yeah. So it's like concatenating arrays, the same thing. Just get a bigger array with all of the numbers from two previous arrays. The same thing. Okay. Is the question because append in Python means the other thing? Yeah. So I think append in Python just adds an element into the array, right? That's where confusing. Okay. Yeah. I mean, append is very confusing name because different languages use it for different things, unfortunately. Yeah. So I mean, in Haskell, there's an infix operator called plus plus. That's why you probably didn't have a confusion there. But and when you want to append many lists, it's called concat, not append. So probably Haskell has a little bit better naming there. But I think in both Racket and Prolog, you have append defined like this. So again, the idea is that you really glue the list together. You're not putting one list into the other. Okay. Now, does the definition make sense to you? I mean, the first two lines. Okay, very good. Now, here we do not use any sort of one-directional predicates. So we actually can use variables in places of the arguments. So what we called arguments, we can just have those as outputs, and what we had as an output, we can just have as an input now. So when we say append x, y, 1, 2, 3, what we mean is, well, give us all possible lists x and y, that if we append them together, concatenate them, then we get this list 1, 2, 3. And the way we defined our predicate actually works really fine because, well, we can see that the first line does not work because y, well, the first line actually can work, right? If y is the entire list 1, 2, 3, then x is the empty list, right? And that gives us the first solution, right? So we get the first solution from the first line of our definition. Now, if we want another solution, we backtrack, try the second definition, and then we know that, well, x now has to have as its first element, the first element of the result, which is 1, and then we do the recursive call. And in the recursive call, again, the first thing that we try is the first line. So the second solution that we get is 1 and 1 and 2, 3, which again, yeah, typos happen. But you understand, right? It's going to be 1 and y is going to be 2, 3. And then, of course, when x is 1, 2, you get 1, you get 3, of course. And then if x is 1, 2, 3, then you get an empty list. Okay. And there are no more solutions. So these are all. So again, this is, you can use append not only to append to lists, but also to take them apart in all the possible ways. Okay, now we'll talk about reverse. So reverse is easy, right? You just take a list and you change the order in which the elements are in that list. So if the list is empty, reversing it is very easy. If it is not empty, however, what do we do? So how do we reverse a list that is not empty? Yep, that's one possibility. So we know that we want to do the recursive call, right? So we reverse the tail of the list and we get some reversed reversed tail, which I will call x here. Okay, so x is the reversed tail. Now, how do we get the reverse of our original list if we know that its head was h and its reversed tail is x? Yep. So we take x, we take the head, and we put it into a singleton list, right? We append those, which effectively puts h at the end of the list x. And that is going to be our result z, which we are going to return. Okay. So unfortunately, this does not work very well, meaning that it's not efficient. I mean, we're not really that much concerned with efficiency in Prolog, but this is like a very simple place to be a little bit more efficient. So if we try to reverse a list ABC, then what happens? Well, we know that the list is not empty, so we definitely are using the second line of the definition, right? Which means that now what we need to do is we need to figure out what is the reverse of BC and then append x1. X1 is going to be the reverse of BC and append A to the end of it, right? And then that's going to be our result. So now our first goal is to reverse BC, which again just means that we need to reverse a single list containing C, then append B to the end, and then append A to the end. Right? Now that of course means that we need to reverse an empty list, and then append C to the empty list, and then append B to the result of that, and then append A to the result of that. Now, reversing an empty list is very easy, right? It's an empty list. So we simplify our goal. Now we need to just append C to the empty list and then do all of the other appends. Now we do that easily, right? Append for an empty list is a very simple equation. It's the first line of the definition of append. But now we get this singleton list, right? And we need to append B to it. Now, when we call append here, of course, we get CB, which is the correct answer, but that's not the point. The point is that we now have to do the recursive call of append, right? One time, but still we have to do it. So we go to the end of this list with singleton list, and then we add B to the end. Now we need to append A to the list CB. Right? So we now have to go to the end of that list to put A in there and return the result. But now, having seen this, you can probably imagine that if the list that we have to reverse is big, right, you would have to do a lot of appends for each element of the list, right? And imagine you have 1,000 elements. Then the last append that you're going to do is going to traverse 999 elements to insert this thousandth element at the end of this list. And the previous append will do 998 recursive calls, right? So the total algorithmic complexity of this append is going to be quadratic, right? Does that make sense? Because you have n number of appends that you do, and each append that you do is linear, right? And of course, the first appends are going to be just append for a singleton list, for a list of 2 elements or 3 elements, but the average size of the list is going to be n over 2, so it's going to be quadratic. Now, this is not ideal. This is not what we typically want. Besides, we know that we can reverse in linear time, I mean, normally, right? So how do we do this? So we do this by using an accumulator parameter, okay? So what is an accumulator parameter? Well, it's the same idea as we've been using in functional programming. Instead of returning the result and then using that result immediately with a recursive call, you have an accumulator parameter where you store essentially the state of your algorithm, right? So what happens here? Here we say that, so we have this second argument, which is the accumulator. The first argument is the list that we want to return, and the last argument is the result. So the first line here tells us that if we want to reverse an empty list and we have already some value in the accumulator, right, then we return that accumulator. So that's going to be our continuously building reversed list. If, however, the input list is not empty and it contains of head and tail, then what we do is we simply do the recursive call with updated state, right? We update the accumulator. Now, the accumulator is already a reversed. Now, remember that this accumulator comes before we got into this, right? So the accumulator is actually the reversed prefix of the list, right? So imagine that you have like a list of numbers from 1 to 5, and you're currently in the middle of the list trying to reverse 3, 4, 5, right? You have already visited 1 and 2, right? And you have already put them in the accumulator in reverse. So you already have as your accumulator the list 2, 1, right? And now you meet the next element in the list, which is 3. Where do you put it? Well, you put it at the beginning of the accumulator, right? And putting something at the beginning of the accumulator is very easy. You just use this the syntax with a vertical bar, right? So let's
can you explain, please, why we put head before accumulator node.
Yeah, let's look at an example, and I think that will clarify things with a lot of you. So we start with an empty accumulator, and we start with a list ABC that we want to reverse. Now, since we know that this list is not empty, we're definitely using the second line of the definition. So, okay, now our accumulator is ACK. Result, well, it doesn't change really. The Z stays the same. We just put head from the first list, from the first argument to the second argument, right? Now, we go into the recursive call. Again, we have a non-empty list on the left. We take the head from it and we put it into the accumulator. Okay. Finally, we take the last bit, put it into the accumulator. And as if by magic, we have a reversed list. And that's the result, right? Okay, does that clarify your question?
Yes.
Okay, very good. Now, you might have seen this already done before with stacks, for example. Remember that singleton list is essentially a stack, which you can pop from the top, right, and push something to the top. So here we have essentially two stacks. We pop elements from one of the stacks and we push it onto the other stack, right? And that's how our accumulator becomes reversed. If you do that with two stacks, you always get a reversed stack. Okay, make sense? Okay. Now with lists, this is especially elegant, but again, the accumulator parameter is a very common pattern that's used in both functional programming and in logical programming. Okay, this is just one example of that. Very good. Do you have any questions? No? Everything is straightforward? Bless you. Okay, then we're a little bit, we're on time. Everything's fine. So your homework would be to read about, so you have already today learned about sort of debugging or understanding how the code runs using trace. Now, there's an alternative way to debug in Prolog, which is an approach which I would like you to read about. So this is your homework, to read about declarative debugging of Prolog programs. And so next time, what we're going to do is we're going to learn cut, or remember what the cut in Prolog is, and learn how to do negation properly in Prolog. Okay, so for now, we're not dealing with negation. Yeah, that's basically it. If you have anything that you did not understand from the lecture, let me know. We have a little bit of time if you want to discuss it. But otherwise, I will see you on Wednesday. Yeah. Okay, custom length function. So n is the length of the list on the left, right? So n is going to be 1 greater than m, right? Does it make sense? So m is the length of the tail, which is, of course, 1 smaller. Any other questions? Okay, very good.